So in today's class, we'll be talking about the second type of connection, which is called as a batt-end connection or a batt-end column. They both are same. So what is this? So if you go back to the concepts of the lacing system, what we have studied was you have the channel sections or you have a particular section. And in order to ensure the safety of this connection, what you're going to do is you're going to provide the lacing systems, right? So why you are providing the lacing systems? Without increasing the area of the members, okay, without increasing the area of the members, within the available area, you are trying to stiffen the members by providing lacings. So it can be a single lacing system or it can be a double lacing system. The other way of doing this, that is the other way of strengthening the members within the available area, is the batt-end connection or the batt-end column. This is a second type of connection. Without increasing the area, you can make sure the strengthening of the members. So that can be done in two ways. The first way is by lacing and the second way is by battening. So this is what we are going to focus in today's class, the batt-end connection or the batt-end column. So in simple terms, what actually the batt-end column consists of is, it consists of a long I sections or the long sections. It can be an I, it can be a channel sections. Okay, so this is column 1 and this is column 2. And these two columns, check down here, these two columns are connected by using plates. You can see plates here, right? These two columns are connected by a plate and these plates are called as battened plates. And these plates are called as battend plates. So that's about the battend connection is. I'll show you the clear-cut image of another image of this one. See, you have the channel sections. This is the first channel section and this is the second channel section. You can clearly see the channel section here. Okay. So these two are the channel sections and the channel sections are connected by using flats, which are ISF, Indian Standard Flats. Here also it is ISF only in the first figure as well. So we are connecting two columns. Instead of providing the lacing system, you are using the plates which are flats, which are called as a battend systems. Battend systems are the battend connections. So when two columns are connected by using a battend plates, such kind of connection is called as battend connection and the corresponding column is called as a battend column. Now you might have a question that where shall we use the laced connection and where shall we use the battend connection? There is no strict rule that only at these places you have to use the laced connection and only at these places you have to use the battend connection. It all depends on the type of the load or the structure where you are constructing. Suppose if you are constructing a structure which is highly exposed to wind, such as transmission towers, at those places you will go for a combination of both the lacings and as well as the battenings. Most probably we will be preferring the double lacing system or the single lacing system. It depends. Again, there is no strict rule for that one. Okay, so this is the second type of connection which we are going to see, which is called as a battend connection. So here the terms which you have to remember are, you are going to provide the battend connection. Okay, you are going to provide the battend connection in two ways. One is called as a end battens, and the other one is called as intermediate battens. Intermediate battens. Now, what is this end battens? End battens are the battens which are provided at the ends of the column. End battens are the battens which are provided at the ends of a column. Suppose if you consider this as the total height of the column, so the end battens are provided at the extreme ends of the column. Okay, whereas the intermediate battens, which is this one, intermediate battens are provided in between the end battens. So there can be number of intermediate battens, but end battens are always two, because one is provided at the top end and the other is provided at the bottom end. And the intermediate battens are the battens which are provided between the end battens, two end battens. And these plates are called as battened plates. Okay, as you see in the figure, these plates are called as battened plates. And this is what you're going to design in this problem. I mean, in the design of backend connections. Okay, so let's look at a problem which talks about how to design a backend connection, and then we'll understand what are the key parameters in that. So here you look at this problem, design a built-up column which is of 9 meters long to carry a factored axial load of 1100 kilonewtons, and the column is restrained in position but not in direction at both the ends. Okay, this is the end connection of the column. The column is restrained in position but not in direction at both the ends, and design the column with connecting system as battens with bolted connections. That means you have to use the battened plate connections and you have to provide the bolted connections only. It's not a welded connection. And here they have clearly mentioned use two channel sections which are placed back to back. And you know what do you mean by back to back? Back to back is this one. So two channel sections which are placed back to back. So this is the problem. So first let's talk about the steps which are involved in the design of the battened connection, and then I'll solve the problem. Okay, so here if you look at the problem, clearly they have given the length of the column, that is 9 meters, and the factored load of the column, which is 1100 kilonewtons, and the two channel sections, right? Apart from these, let's find out what are the various steps that are involved, and then we'll look at the solving. So the steps that are involved here are, the first step is, here you don't know what is the size of the column, right? You need to decide the size of the column. So in the first step, what you're going to do is design of column section, design of column or column section. I'll write it here, design of column section. Now, how will you design a column section? You're going to design the column section by obtaining the area value. Okay, so you'll calculate the area value, that is area equals to factored load by the permissible stress. So that I'll talk. So the permissible stress, you can make it as permissible, this one, permissible stress. So based on the area obtained here, you're going to select a channel section. Okay, based on the area which you are obtaining here, you're going to select a channel section, and then you're going to choose that channel section. And now whatever the channel section that you have selected here, okay, whatever the channel section that you have selected here, it must carry a load of 1100 kilonewtons. That means you have to check whether the channel section which you have selected is carrying enough amount of load or not. How will you check? You're going to check by using this formula, that is design compressive strength, that is PD equals to AE into FCD. You know how to calculate the value of FCD. It is based on the buckling curve, right? That, however, I'll talk about when we are solving the problem. So this is the first step. So once you designed the column section, and remember here, whatever the value that you are obtaining, it must be greater than the factored load which is given in the question. So the factored load given in the question is 1100 kilonewtons. Okay, if it is greater than 1100 kilonewtons, then the column section which you have selected is safe. This is the first part. The second part is you have to find out the spacing of channels. You have to find out the spacing of channels, that is S. So in the last class, we have solved about how to find out the spacing of channels. We have a formula that is 2 times of Iz equals to 2 times of Iy plus A into S by 2 plus Cyy whole square. From this formula, you're going to obtain the spacing value, that is spacing of channels. Now, we also have to find out the spacing of battens. Okay, spacing of battens. Let's just consider this as C as the spacing of battens. So we have different conditions for that. So let's solve that while solving the problem. So the next step is spacing of battens. And the fourth step which you're going to find out is the size of end battens. What should be the length and what should be the thickness and what should be the depth of the end battens. Okay, the size of end battens. So what you're going to find out is the length, depth, and the thickness. So these are the three things which you're going to find out. And we are also going to find out the size of intermediate battens. I have talked to you already that we are going to provide the battens at the ends of the column as well as at the intermediate portions. So here also you are going to find out length, depth, and thickness of the intermediate battens. So now once you design the end battens and the intermediate battens, what you're going to find out is we are going to find out the forces in the batten section. So that is design forces. We are going to find out the transverse shear, that is VT, and we are also going to find out the longitudinal shear, which is VB, and then the moment which you are going to find out. So for this, corresponding checks will also be there. Okay, you're going to check whether the VT, that is transverse shear, longitudinal shear, and the moment are sufficient enough or not. And then as the last part, you're going to find out the connections. That means you're going to find out what are the number of bolts and how many number of batten plates are required. All these things you're going to find out. So this is what, in simple terms, the steps which are involved in the design of battened connection. So in simple terms. So let's solve the problem. Okay. So what is the first step which we have talked is you have to find out the design of column or design the column. So before designing the column, let us write the given data and then let's start solving. So the given data is given data, that is length of column, which is 9 meters, and the axial load or the factored axial load, you make it as factored axial load, which is given as 1100 kilonewtons, and the end conditions are also given, that is column is restrained in position but not in direction at both ends. Okay, you know the table number and you refer the table and then find out the corresponding value of K. That, however, I'll find out later. Okay, so you're going to provide the battened connection. You're going to provide the battened connections, providing two channels by using two channels which are placed back to back. So this is the key data which is provided in the question. Okay, now let's find out the value of K. Okay, so if you remember the table number, someone please tell the table number of to find out the value of K. So the condition, the column ends condition. So what is the condition that is specified? It is restrained in position. Page number. Anyways, so the column ends condition are restrained in position. Just a minute. Restrained in position, but not in direction. This is what they have specified. So now from table 11 of IS 800 2007, from table 11 of IS 800 2007, can somebody tell what is the value of K? Okay, what is the value of K when the column end conditions are restrained in position but not in direction? So here from table 11 of IS 800 2007, the value of K is 1. So therefore, the effective length, that is KL, equals to 1 into what is the length of the column? It is 9 meters, which will be 1 into 9 will be 9 meters. And here, let us assume the axial compressive stress. Assume the axial compressive stress. Axial compressive stress as 150 newtons per mm square. So let us assume the axial compressive stress as 150 newtons per mm square. So therefore, the cross-sectional area required for column. Okay, we are designing the column only. So the cross-sectional area required for column, that is area required, equals to factored load upon axial compressive stress. Upon axial compressive stress. Okay, so what is the factored load? It is given in the question, which is as 1100 kilonewtons. So 1100 into 10 cube. And the axial compressive stress we have assumed as 150 newtons per mm square. That is 150. So if you solve for this one, the area required is obtained as 733 mm square. Now, this is the amount of area which you have to provide for the column section. Now here, when you are providing the column section, it is clearly said that you are going to use the 2 channel sections. That means this area, that is 7333 mm square, is the area of 2 channel sections. Okay, but we need. So here we know that the area required, that is 7333 mm square, is the area of 2 channel sections. So let us get the area of 1 channel section. Okay, so the area of 1 channel section equals to the total area, that is 7333 upon 2. So the area of 1 channel section will be 3666.5 mm square. So this is the area of 1 channel section. Now what you have to do is you have to refer steel tables book and find out a channel section which has an area greater than 3666.5 mm square. Okay, the condition is you have got the area of the channel section. Now your idea is to select a channel section. How you're going to select a channel section? It is by looking at this area. Okay, so now let us find out that from steel tables, okay, let us try 2 ISMC 300 at the rate 351.2 Newton per meter, which has an area. So if you check down the area of ISMC 300, which has an area 4564 mm square. 4564 mm square. So it is greater than the selected value. So which has an area 4564 mm square. So therefore, the sectional properties of ISMC 300 at the rate 351.2 Newton per meter are. So let's write the sectional properties. So the area value is 4564 mm square. Okay, and then the Ry value, that is radius of gyration, is 26.1 mm, and Rz value is 118.1 mm, and Iz, that is moment of inertia along ZZ axis, is 6362.6 into 10 power 4 mm power 4, and Iyy value is, that is moment of inertia along YY axis, is 310.8 into 10 power 4 mm power 4, and Cyy is 23.6 mm, and the width of flange is 90 mm. You can also write the height of the section, which is 300 mm. If you want, you can also write the width of a web and the thickness of the web. Okay, sorry, thickness of the flange and width, thickness of the web. So that we'll write when we need. Anyways, so this is the section which we have selected, right? So now what is the area provided? Area provided equals to, we are providing 2 channel sections, and what is the area of 1 channel section? It is 4564. So the area provided for the 2 channel sections equals to 9128 mm square. But how much you can provide? It is 7333 mm square, but you are providing more than that, which will be safe. So this value is greater than 7333 mm square. Therefore, the selected section you can make. The selected section is appropriate. Okay. Suppose, say for example, here instead of 9128, if you are getting 6584, some random value. So this is less than 7333 mm square, right? What is the condition is the area required. Okay, you can make it here. The area required. Okay? The area required must be, that is the value of 7333 mm square must be, or you can also make it in this way, that is area provided must be greater than area required. Okay, this is the final condition. The area provided must be greater than the area required. If this condition is satisfied, then the section whichever you have selected will be safe. Anyways, so now the section which you have selected is appropriate. Now what you have to find out, you have to find out one thing, which is we have found out the area now, and we have also selected the section. Now we need to find out the design compressive strength. Okay, so how will you find out this one, design compressive strength? So let's find out that one. So the design compressive strength, design compressive strength. So in the same step, you can make this one. So the design compressive strength is generated with PD, which is AE into FCD. Now, in order to find out the value of FCD, remember, in order to find out the value of FCD, you need to have the value of KL by R, that is slenderness ratio. So let's find out that one. So directly I'm finding out the effective slenderness ratio. So the effective slenderness ratio, that is lambda E. So how will you find out the effective slenderness ratio? If you go back to the concepts of the laced connection, okay, if you remember the laced connection, the effective slenderness ratio is taken as 1.05 times of KL by R. That is, just a minute. Yeah. So the in laced columns, the effective slenderness ratio is taken as 1.05 times of KL by R. So this is specifically in lacing system. But what we are doing is the battened connection. In battened connection, the effective slenderness ratio is taken as 1.1 times of KL by R. Okay, 1.1 times of KL by R. And here it is R maximum. KL by R maximum. I'll write it very clearly here. KL by R maximum. So remember, don't confuse between the effective slenderness ratio of laced connection, which is this one, and the battened connection, which is 1.1 times. Anyways, so therefore, the effective slenderness ratio equals to 1.1 into the value of K is 1 and the value of L is 9, which is the length of the column, that is 9 meters, upon R maximum. So here you have Ry and Rz. So Ry value is 26.1 and Rz value is 118.1. So obviously you're going to take the highest value, which is 118.1. So this I'm converting into mm. Okay. So if you solve for this one, the effective slenderness ratio is obtained as 83.82. So this is the effective slenderness ratio. Now, what you have to find out is you have to find out the value of FCD. Okay, you have to find out the value of FCD. Now, how will you find? So from table 10 of IS 800 2007, okay, from table 10 of IS 800 2007, the built-up section, belongs to buckling. I'll write down here. Belongs to buckling class C. Okay, all the built-up sections are belonging to buckling class C. It can be an I section, it can be a channel section, or it can be of any type. If it's a built-up section, that means if there is only just the channel section, we have another buckling class. However, it is also C. But if you are providing any extra members in order to strengthen the main members, then such kind of section is called as a built-up section. Okay, it can be an I section, it can be a channel section, it can be a angle section, it can be of any type. So from table 10 of IS 800 2007, the built-up section belongs to buckling class C. Now you might have a doubt that how you're considering this particular problem as a built-up section, because you have two channel sections, and these two channel sections are provided by using a plates which are called as a battened plates. You have end battens and the intermediate battens, right? So if you are providing some additional members in order to ensure the safety of the main members, it's called as a built-up section. Okay. Anyways, so it belongs to buckling class C. Now what you have to do is from table 9C of IS 800 2007, from table 9C of IS 800 2007, for KL by R equals to, what is the value of KL by R? It is 83.82. For KL by R equals to 83.82 and Fi equals to 250 megapascals. Okay, and Fi equals to 250 megapascals. FCD equals to, we don't know this one, right? For KL by R equals to 83.82 and Fi equals to 250 megapascals, you need to find out the FCD value. Okay, that is the design compressive stress. Design compressive stress. Now let's find out, let's look at this table 9C and then let's solve for the FCD value by interpolation. So if you refer table 9C of IS 800, you don't have the exact values of 83.82. You don't have the exact values of 83.82. But what you have is 80 and for 90. So 83.82 lies in between 80 and 90, and that's the reason why I'm taking 80 and 90 values. Okay. Anyways, so if you solve for this one by interpolation, you will get the value of FCD. So therefore, FCD equals to, after interpolation, you will be getting the value as 130.27 newtons per mm square. Right? This is the value of FCD after you do the interpolation for this one. So therefore, the design compressive strength, that is PD equals to, you know the formula, that is AE into FCD. What is AE? It is the area. Now, how will you find out the area? It is the area of two channel sections. It is not the area of only one channel section. What is the area of two channel sections? It is 9128 mm square. So 9128 area of two channel sections. Remember, it is not the area of one channel section. It is the area of two channel sections. And what is the value of FCD? It is 130.27. Okay. So if you solve for this one, you will be getting the answer as 1189.1 kilonewtons. And what is the condition? This value must be greater than the factored load which is given in the question. So what is the factored load given in the question? It is 1100 kilonewtons. So this value is actually greater than 1100 kilonewtons. Therefore, safe. Okay, or you can make it here only. So safe. So the section which you have selected is able to carry a load greater than 1100 kilonewtons. Okay, so that's how you can select the section. This is all the first part of the section. Now what is the second part? It is the spacing between the channels, spacing of channel sections. So let's solve for the second one, that is the spacing of channel section. Second step is spacing of channels. So let us consider, let S be the spacing of channels. So let S be the spacing of channels. And here you are providing the two channel sections back to back. And this spacing you are considering it as S. So how will you find out this one? So if you refer the lacing system pattern, you have the formula that is 2 into Iz equals to 2 into Iy plus A into S by 2 plus Cyy whole square. And you have all the values of Iz, Iy, A and Cyy. So from this you can get the value of the spacing between the channels. Now, so therefore the spacing of the channel section S equals to 184 mm. So this is the spacing of the channel sections. Now what is the next step? Next step is spacing of battens. Okay, so you're going to provide the batten plates. So let's find out what is the spacing of the battens. So how will you find out the spacing of the battens? Is you have some certain conditions are available for this. So the first condition is C by Ry, or you can say it as R minimum. C by R minimum should be less than 0.7 times the slenderness ratio of the column. Okay, C by R minimum should be less than 0.7 times the slenderness ratio of the column, or you can say it as effective slenderness ratio. Okay, so let's find out the value of C, or you can make a statement here. Let C be the spacing between battens. Let C be the spacing between battens. So you know all the values, you know the value of slenderness ratio and R minimum. So C should be less than 0.7 times the effective slenderness ratio. What is the effective slenderness ratio? That is lambda E. It is 83.82, right? So it is 83.82 into R minimum. What is the value of R minimum? It is 26.1. And if you solve for this one, you will be getting the answer as 1531.39. 1531.39. Also, you have another condition. This is the first condition. And the second condition is C by R minimum should be less than 50. Should be less than 50. So from this, and C should be less than 50 times of R minimum. That equals to 50 times of 26.1. So which will be 1305 mm, and this is 1531.39 mm. And now you have got two spacing values. That is, the first one is 1531.39 mm and the second one is 1305 mm. Okay, so now which one you have to consider? Let us consider the spacing value which is having the less spacing. Okay, so consider the value of the spacing between the battings as the one which is having the less spacings that you are going to consider. That is what it says. So therefore, the spacing of battens, that is C, equals to, you can take it as 1305 mm, or you can also take 1300, or it's okay if you can take the 1310 also. But instead of taking 1305 or 1310, if you take 1300, it will be better for the calculation purpose. And again, here there is no strict rule that you have to go for only 1300. You can select the same value of 1305, or you can go for the a little greater value of 1310, or you can also come down to 1300, which is more or less same. But however, there is no strict rule that you should only consider 1300. If we consider 1300, it will be better for the calculation purpose. Apart from that, there is no other thing. So therefore, the spacing of the battens, I'm assuming it as 1300 mm, or you can solve for same value, that is 1305 mm also. You don't get a major difference between 1305 mm and 1300 mm. Okay, that's the reason why I'm taking here. Anyways, so let us consider the spacing of battens as C equals to 1300 mm. Now the next step is the size of the battens. Size of battens. So how will you find out the size of the battens? We have certain conditions for this. Okay, so technically here it is the size of end battens. You can keep it as size of end battens. So here, since they haven't specified anything about the diameter of bolts, use 20 mm bolts. Okay, use 20 mm bolts of 4.6 grade. Let us use 20 mm bolts of grade 4.6. Now, you know the batten plates will be like this. Okay, you know the batten plates will be like this. So let us consider this as L, which is length, and this is depth, and you also have the thickness. Okay, length, depth, and thickness. So let's find out each one of these values. Initially, let's find out the effective depth. The effective depth. So effective depth is usually denoted with D dash. So the effective depth equals to spacing plus 2 times of CYY. This is the fixed formula. Spacing plus 2 times of CYY. So here we have got the spacing value as 184 mm. So for calculation purpose, let us take the spacing value as 200 mm. It is just for calculation purpose. You can take the same value of 184 mm. In the last problem, that is in the design of lacing connection, we have taken the spacing value as 184 mm only, and then we solve. Here also you can take 184 mm only, but for simplification of the calculation purpose, I am taking it as 200 mm. Remember, there is no rule that I should go for only 200 mm. You can also take 184 mm and then solve. Okay. Anyways, so let us take the value of spacing as 200 mm and then let's solve this one. Therefore, the effective depth, that is D dash, equals to 200, which is the spacing, plus 2 times
184 this.
So the CYY value is 23.6. So therefore, D dash equals to 200 plus 2 times of 23.6, which will be 247.2 mm. And this D dash value must be greater than 2 times of width of flange. 2 times of width of flange. This is the condition. So what is the width of flange? It is 90 mm. So which will be 180 mm. So obviously the condition is getting satisfied. Therefore, the effective depth which you have selected is safe. Now, let's find out the overall depth. Overall depth. You can denote with this with capital D or small d. It can be anything. So let us make it as small d or capital D also. That's up to you. So the overall depth equals to effective depth, which is d dash, plus 2 times of edge distance. Effective depth plus 2 times of edge distance. Is it okay if I continue for half an hour more so that I can finish this problem? Is it okay for everyone? Someone, if you can respond, then I can decide whether to stop the class or to continue. Is it okay if I continue the class for half an hour more?
For me, okay, sir.
Okay, fine. How about remaining students?
Okay for me.
Okay, fine then. Fine then, I'll continue. Yeah, therefore, the size of intermediate battens. So here also you have to find out the effective depth, overall depth, the thickness values. So let's find out the effective depth initially. The effective depth of intermediate battens. The effective depth of intermediate battens, which is, you can say this as D1 dash. So here the end battens you are taking it as D dash. So here let us take the value of effective depth of intermediate battens as D1 dash. So the D1 dash can be found out as 3 by 4 times of D dash. Okay, so 3 by 4 times of D dash. And what is this D dash? It is the effective depth of intermediate battens.
Sorry, one fixed formulas, sir.
Yes, they are all fixed formulas.
Code book laite levu.
D dash, where 3 by 4 times of D dash value is 247.2. Okay, this is what we have solved. So therefore, this value is 185.4 mm. And again, this value should be greater than 2 times of width of flange. So the width of the flange is 90 and it will be 180 mm. So which is again the safe condition. And now we have to find out the overall depth of the intermediate batten. The overall depth of intermediate batten. So here also I'm taking it as D dash. Okay, there it was D. So here I'm taking it as D dash. So therefore the overall depth of the intermediate batten equals to D1 dash plus 2 times of edge distance. Same as in the previous case. So the D1 dash is 185.4 and 2 times of edge distance is 35. Okay, we got it as 33. So I'm taking it as 35. You can also take 40 as well, no problem. So I'm getting this as 255.4 mm and I'm approximating this value to 260 mm. So this is the overall depth of the intermediate battens. And now let's find out the thickness of the batten. The thickness of intermediate batten. So the value of T can be found out as, that is the thickness of the intermediate batten can be found out as the same formula, that is 1 by 50 times of spacing plus 2 times of pitch distance. 2 times of pitch distance. So that will be 1 by 50 times of the spacing value is 200. Okay. See, remember whenever I'm representing S, it is the spacing between the channels. If I'm representing C, it is the spacing between the battens. Don't confuse between S and C. So plus 2 times of pitch distance is 50. And which will be the value of thickness will be 6 mm. And the thickness of the batten, intermediate battens will be 6 mm. So therefore, the size of intermediate battens equals to, you have got the length as, okay. Now what is the overall depth? It is 185, sorry, it is 260 mm, and the length will remain same, that is as we have calculated in the previous step, that is L equals to S plus 2BF. The length will remain same, the length does not change, because the length whatever is here at the top, at the bottom, the same length will be there at the intermediate, and the same length will be continued throughout the spacing. Okay, so that's why I'm placing the same length, which is 380 mm divided by 260 mm divided by 6 mm. So this is the size of the intermediate battens. So now we have designed the end battens and the intermediate battens, and let's find out the forces in these members. So the design forces. So the design forces are, the first one is the transverse shear, same as we calculated in the design of single lacing system. The transverse shear is taken as 2.5% of axial load, same as the lacing system connection. So 2.5 upon 100 into 1100 newtons, which will be 27.5 into 10 cube newtons. And the longitudinal shear, which is VB equals to, so how will you find out this longitudinal shear is VT, which is the transverse shear, into spacing between the battens upon 2 times of spacing, okay, plus 2 times of pitch distance. Well, this is a fixed formula. So what is the value of VT? It is 27.5 into 10 cube. And the value of C, which is the spacing between the battens, it is 1300 mm upon 2 times of S, which is the spacing between the channels, which is 200 mm, plus 2 times of pitch distance is 50. So this will be 59583 newtons. So this is the longitudinal shear. And let's find out the value of moment, which is capital M. Moment equals to Vt, okay, so the value of Vt into C upon 4. This is the fixed formula. Vt into C upon 4. So the value of Vt is 27.5 into 10 cube upon, into 1300 upon 4, which will be 8937500 Newton mm. 8937500 Newton mm. So this is the moment. Now you have got the transverse shear force, longitudinal shear force, and the moment. Now we have to check whether these transverse, longitudinal, and moments are in safe conditions or not, especially for end battens. We also have to check for intermediate battens, but let's check for end battens initially. So in the same step, you can make a heading as check, and this check is for end battens. We will also check for intermediate battens as well. Check for end battens. So the shear stress equals to, the formula is VB upon the width of end battens. You can make it as BEB. EB represents end batten. Just for your understanding purpose, I'm writing it as EB multiplied by thickness of the end battens. Okay, so VB value is 59583, which is here, 59583 upon the width of end batten is 320 and the thickness of the end batten is 6. So this will be 31.03 newtons per mm square. And remember, this value must be less than Fy by root 3 into gamma m naught. This value must be less than Fy by root 3 into gamma m naught, where Fy is 250 and the root 3 into 1.1. And if you solve, you will be getting the value as 131.2 newtons per m. Just check this value and let me know. I'm getting it as 131.2 newtons per mm square.
131.21, sir.
Okay. So therefore it is safe. The shear stress is safe. That means 31.03 is obviously less than 131.2 newtons per mm square. Now we also have to check for bending stress. Bending stress. So the bending stress formula is 6m upon TBEB square. That is the thickness of the end batten into width of the end batten square. I'll just write down in this way: thickness of end batten into width of the end batten square. So which will be the moment equals to 6 into 8937500. This is this one, the moment 8937500 into the thickness of the end batten is 6 and the width of the end batten is 320 mm square. 320 square. So this is 87.27 newtons per mm square. And remember, this value must be less than Fy by gamma m naught, where Fy is 250 and gamma m naught is 1.1. So this is 227 newtons per mm square, which is safe. So the bending stress is also safe for the end battens. Similarly, we also have to find out for the intermediate battens. So let's solve this step and then we'll solve the remaining things in the next class. So for intermediate battens. So here also we are going to find out the shear stress as well as the bending stress. So the shear stress value, I am just writing down the values, that is 59,583 upon 260 into 6, which is the width of the intermediate batten upon into thickness of the intermediate batten, which will be 38.15 newtons per mm square, and this value should be less than Fy by root 3 into gamma m naught. It will be, however, less than this value. You can also check later. So which is safe. And the bending stress has also to be checked. Bending stress equals to same formula, which is 6m by thickness of intermediate batten into width of intermediate batten. IB represents intermediate batten square. Okay, so if you solve for this one, you will be getting as 132.2 newtons per mm square. And remember, this value must be less than Fy by gamma m naught. This value must be less than Fy by gamma m. So if it is less, then it is safe. Okay. Now let's proceed to the next step, which is the design of connections. So in connections, when you are doing connections for the battened columns, you have to do the connections which should be designed for to transmit both the shear force as well as the bending moment. So therefore, let's write this statement, that is the connections should be designed to transmit both shear and bending moment. Both shear and bending moment. So whatever the connections you are doing, it must be designed to transmit both shear and bending moment. So since we don't know the diameter of the bolt, let us assume using 20 mm diameter bolts using 20 mm diameter bolts of grade 4.6. Okay. Now let's find out, we need to find out the number of bolts value. So the number of bolts can be found out by factored load by bolt value, where bolt value is the least of strength in shear, that is VDSP, and strength in bearing, which is VDPB. So now let's find out the strength in shear and strength in bearing values. So initially I'm finding out the strength in shear, which is VDSP equals to VNSB by gamma MB, where VNSB formula you know, which is FUB by root 3 NN ANB plus NS ASB. So here I am considering NN value as 1 and NS value as 0. Okay, into 1 by gamma MB. So this is the condition, that is NN equals to 0 and NS equals to 1. So if you solve for the values, then you will be getting the design shear strength, that the value as 45.26 kilonewtons, that is VDSP value. And similarly, you are also going to find out the value of VDPB, that is design strength in bearing, which is VNPB by gamma MB. Now, in order to find out the VNPB value, you know the formula, that is 2.5 kb dt into fu into 1 by gamma MB. Where again, in order to find out the value of kb, you have the conditions, that is E by 3D naught, that is kb value is the least of 3 conditions, that is E by 3D naught. Next one is P by 3D naught minus 0.25 and FUB by FU and 1. So you can solve for the values of VDPB, where you'll be getting the VDPB as 96 kilonewtons. 96 kilonewtons upon solving all the values. And here the end condition, edge distance and the pitch distance you might have an aware, that is 1.5 into D naught and 2.5 into D, where D is the diameter of the bolt and D naught is the diameter of bolt hole. So therefore, bolt value equals to, so bolt value is the least of shear and bearing, which will be 45.26. So this is the bolt value. So this is the bolt value. And here you have to remember the value of T is the thickness of the batten plates, which is 6 mm. Okay, the value of T is the thickness of the batten plates, which is 6 mm. So therefore, let's find out the number of bolts required. So number of bolts required, that is N equals to factored load by bolt value. So the factored load is VB, okay, upon bolt value is 45.26, where VB value we know, which is 59583 newtons. So you can find out the VB value here only. So which is the longitudinal shear, that is this one, 59583 newtons. And the bolt value can be taken as, this is also converted into newtons, that is 45.1026 into 10 cube newtons. So which you will be approximately getting as 1.31 bolts. So I'm taking these bolts as 3 bolts. So I'm rounding off 1.31 to 3 bolts. Okay. So here there is a reason that instead of taking 2 bolts, you might have doubt that why can't we take 2 bolts instead of 3? So the reason for this is the increase in number of bolts. Okay, we are increasing the number of bolts to 3. It is basically to account the bending moment. Okay, it is basically to account the bending moment. So that's the reason why I'm increasing it to 3 instead of 2. So the reason why I'm increasing the number of bolts to 3 is to account for the bending moment. Okay, now let's find out the another condition, that is these bolts, these 3 bolts are provided in a vertical row. Okay, provide 3 bolts in a vertical row. So we know we are providing 3 bolts in a vertical row. Now we should find out what is the pitch distances between these bolts. Okay, let's find out the pitch distance. Vertical row at a pitch of, or at a pitch of, okay, how will you calculate the pitch of battened connection bolts at? It is equals to half of, it is equals to half of width of end batten plate, width of end batten plate, okay, minus 2 times of edge distance, minus 2 times of edge distance. So this will be half of width of end batten plate. So let's go for the condition and check for what is the width of the end batten plate. So the width of end batten plate is 320 mm. Width or depth, anything is same. So width of end batten plate is 320 mm. Okay, or you can write it here only, that is instead of width you can write it as depth of end batten plate, where depth of the end batten plate is 320 minus 2 times of edge distance is 35 mm. So this will be 125 mm. Let us consider this as the value of R. Let's take this as R. Okay. Now let's find out what is the force in each bolt due to shear. So force in each bolt due to shear. So how will you find out this force in each bolt due to shear? It is actually the values of number of bolts, that is 3, okay, that is can be calculated as VB upon number of bolts. And let's look at what is the value of VB. So it is the longitudinal shear, which is 59583. Okay, so VB upon number of bolts. So the VB value is 59583. 59583 upon 3, because we have provided 3 bolts here. Okay, and I have also said that why we are providing 3 bolts instead of 2. It is because of to account for the bending moment. So now we are going to calculate what is the force in each bolt. Therefore, the force in each bolt due to shear is 19861 newtons. So this is the force in each bolt due to shear. Similarly, the force in each bolt due to bending moment, this also has to be calculated, because on the bolts both shear force as well as the bending moment will be acting. So how will you calculate? We have a formula for this, which is M, that is moment into R upon summation of R square. So what is the moment value? We have solved it here. So the moment is obtained as 8937500. This one, 8937500, which will be 8937500 into R. What is R? It is 125, which we have calculated here. 125 by summation of R square. So summation of R square is nothing but 125 square plus 125 square. So you know the value of R. Okay. So 125 square plus 125 square. Now why, you might have a question that why I am taking 125 square plus 125 square. Suppose we are providing 3 bolts, right? So how many values of R you have? So here R is 125 mm, that is the pitch distance. So you have 2 values of R, right? So that's the reason why I am taking 125 square for the first 2 bolts and 125 square for the second 2 bolts. Okay, I hope it is clear. So if you solve for this one, then you will be getting the force in each bolt due to moment as 35750 newtons. 35750 newtons. Now let's find out the resultant force. Resultant force That is, you can make it as R, the resultant force, or you can just keep it that way itself. Resultant force equals to force in each bolt due to shear, that is 19861 square, plus force in each bolt due to moment square, that is 35750 square. So if you solve for this one, you'll be getting the answer as 40896.47 newtons. And remember, this value must be less than 45.3 kilonewtons. So it is actually the less than the bolt value. What is this 45.3? It is bolt value. Okay. So here it is, obviously it is less than that. So here 45.3 is in kilonewton. So if you multiply with 1000, obviously 40896 is less than 45.3 kilonewtons. So which is safe. Now let's find out how many number of battened plates are to be provided on one side of the column. Okay, so you have the column section and you are going to provide the number of battened plates, right? So how many battened plates you are going to provide on one side of the column channel section. So you have the channel section here, right? How many batten plates are to be provided? So let's find out the required number of batten plates. So therefore, number of batten plates, on one face. That means you have two faces. You have the front face as well as the back face, right? So this can be calculated as length of column upon spacing of batten, plus 1. This is the formula. So the length of the column is given in the question, which is as 9 meters. So I'm converting into mm. That will be 9000 mm. By spacing of the battens, we have found out, which is 1300 plus 1. So if you solve for this one, you will be getting as 7.92. So approximately I'm taking as 8. So therefore, provide 8 battens or batten plates, 8 batten plates on each face of the column section. And this is how the entire design process looks like. Okay. So the diagram goes in this way. The connection diagram goes in this way. That is, you will have the channel sections. Okay. You have, let's draw in this way. So you have the channel sections which are placed back to back. So these are the two channel sections which are being placed back to back. Okay, obviously you'll be having in this way. And the detailing goes in this way. So you have the two channel sections and you know the center to center spacing between the channels, which is S. Okay. Anyways, now how does the batten plate arrangement looks like? Okay. So if you see from the front view, how does this looks like is this is the top view actually. Okay. So if you see from the front, how does they look like is they looks in this way. A single long column which is of 9 meters length. Okay. It is of 9 meters length. Now here we are going to provide the battened plates. Okay. So we have got two types of battens. One is the end batten and the second one is the intermediate batten. Okay. So the size of the intermediate batten is 380 by 260 by 6. Okay. and the size of the end batten is 380 by 320 by 6. So you're going to provide, suppose if you consider this as the end section, say consider here you have the continuation part. Here you can say it as the end batten along this side. This entire portion is the end batten plate. Okay, where you have 3 bolts on one side. Well, likewise, you have 6 bolts. So similarly, you also have the intermediate battens. So the intermediate battens will be somewhere here. You can say since the column is continuous, I'm drawing here itself. Okay, this is the intermediate batten. Again, for the intermediate batten also, you are having 3 bolts on one side. So this is the intermediate batten. You can write down the sizes of the batten plates also, both the intermediate and the end batten. So this is the end batten. Okay, so here also you can make it as intermediate batten plates or end batten. So this is the entire design of the connection. So make sure of writing what is the type of the channel section and what are the dimensions of the end batten and intermediate batten along with the diameter of bolts. So obviously we are using 20 mm diameter bolts. So write down all the specifications that are required for you. So in the next class, we'll be talking about the another problem. Thank you.